let's examine the units of the acceleration vector in polar coordinates. First, I'm going to write down this big expression that is written in terms of r hat and theta hat. Those are the unit vectors for polar coordinates in 2 dimensions. So on the left-hand side, I'm going to write a for acceleration. I'm going to put a little arrow on top to signify that it is a vector quantity. And this is equal to, we're going to have 2 big components. And each of those components are going to have 2 terms. So we're going to have 4 terms in total that we need to analyze and make sure the units are all consistent. So we're going to do some dimensional analysis. So let's get started. First, let's have a look at the radial component. So I'll put this in some brackets. The first one we're going to have is r double dot. So the second time derivative of r. Then we're going to subtract from that r theta dot squared. This is r theta dot squared. And this is all in the radial direction. So this is pointing in the r hat direction. This is all scaling the unit vector in the radial direction. This term over here, this is actually analogous to the Cartesian coordinate system. We're just taking the radial distance and we're differentiating with respect to time twice. So we're taking 2 time derivatives. That's why there's 2 dots over here. It's r double dot. This term over here has a minus sign, and it is associated with the centripetal acceleration, which is the acceleration that points towards the center. So if r hat points away from the center along the direction of the radial vector, then this guy is pointing in the opposite direction. It's pointing towards the center. So if some particle is going around some kind of origin of the coordinate system, this is pointing towards the origin of the coordinate system. So this is the centripetal acceleration term. Now let's introduce the final 2 terms. So I'm going to write over here, I'm going to have plus, we need 2 more terms. We're going to have one term that has a factor of 2, it has an r dot and a theta dot. And this term is actually associated with the Coriolis effect. So the Coriolis effect originates with this term over here. And we're also going to have one more term, and that term is going to have r multiplying theta double dot. So the double dot is taking the time derivative twice. So we're taking the time derivative of the angle twice. And this is all in the theta hat direction. And the theta hat direction is the tangential direction. So this is in the radial direction, and this is in the tangential direction. So those are the 2 unit vectors that we're using for polar coordinates in 2 dimensions. So we're not looking at 3-dimensional motion over here. This is just 2-dimensional motion. So it's motion in the whiteboard. It's in a plane. And these are the unit vectors that we're using to construct any vector. And specifically in this video, we're talking about the acceleration vector. In the previous video, we did dimensional analysis for the velocity vector in polar coordinates as well. And we found that all the terms were dimensionally consistent. Let's do the same for acceleration. So acceleration has some very interesting units. If we start off with position and we differentiate it, we get velocity. And if we differentiate velocity again, we get acceleration. So we're taking 2 time derivatives. Every time we take a time derivative, we're actually dividing by a little infinitesimal time increment, delta t. And we're taking the limit as delta t goes to 0. So when you divide by that tiny little infinitesimal increment of delta t, and you actually introduce a unit of per time. So you're dividing by a unit of time. So you're taking the difference of 2 vectors and then dividing by a little delta t, and that introduces that extra unit. So this guy over here, because we're differentiating twice, has 2 extra units of time in the denominator. So let's write that down. We have a unit of length and 2 units of time that we're dividing by. So it's length per time squared. Or in SI units, if we write this in SI units, we have meters per second squared, or meters per second per second. Another way of writing it is meters per second, like this. Or sometimes people like to write it as meters per second and then per second again. So these are the units for acceleration. And I've explained why we have these units of time that we're dividing by. That comes from taking the time derivative. So now let's have a look and see if all these 4 terms over here match. We want to make sure that this is dimensionally consistent. We want to make sure that the units all match when we're adding them together. So let's have a look at this first one over here. This is probably the easiest one out of the 4. This one is a unit of length. So the radial distance has units of length, and we're taking the time derivative twice. What is that going to do? Well, it's going to do exactly the same thing that we just described before. We take something that has units of length, and then we take the time derivative twice. That's going to introduce 2 of these time units in the denominator, and that's going to give us length times time to the minus 2. So this first term over here checks out. Everything is consistent. Now let's have a look at this centripetal acceleration term. So we're going to ignore this minus sign. The minus sign doesn't matter. It's just a constant of -1 multiplying out the front. And constants don't have any units. They're unitless. So these are constants out the front that don't have any units. Some constants actually do have units, and they're introduced into equations to make sure that they're dimensionally consistent. So for example, Coulomb's law has Coulomb's constant, that little k out the front, and that makes sure that everything is dimensionally consistent. But for these little numerical constants like -1 or 2 or 5 or pi, those values do not have any units. They're dimensionless quantities. So now let's have a look at this guy over here. So r gives us a unit of length, right? So the radial distance, that has a unit of length. Theta dot, what is that going to be? Well, I'll put this in brackets. Theta dot has units of radians per unit time, because we're differentiating the angle, and the angle is measured in radians. So we have something that is in per unit time. So I'll write t to the -1. And then we're actually taking that and we're squaring that. And if we square that, that's going to give us exactly the same thing. We're going to get length times time to the -2. We just use those exponent laws. So if we have something that has units of per time, and then if we square that, that's going to give us per time squared. So we have per time squared, length times time to the -2. That is exactly the same units as this over here. So now let's have a look at this guy over here. This guy has a factor of 2. Now, as we said before, this factor of 2, we're not even going to consider that in the units, right? Because 2 is just a numerical constant. Sometimes you have constants that have units, and some constants don't have units. One constant of proportionality that is actually dimensionless is the coefficient of friction. So if you've done some little dynamics problems, you might have come across the coefficient of friction. And that is usually represented by the Greek letter mu. And that is a dimensionless quantity. But it does have a physical significance. It's not just a number like 2, -1, or pi. So you have to be careful with these units. You have to make sure that all of the constants have consistent units. And you can actually do things to expressions to get rid of units. So you can remove units and move them into factors somewhere else. So units are very important concepts in physics. So let's have a look at this guy over here. R dot. R dot is the time derivative of r. So that's going to give us a length per unit time. So it's the same as units of velocity. That's r dot. And then we need to multiply r dot by theta dot. But theta dot has units of per time, or radians per unit time. But we're going to ignore radians because radians are not really treated as meters or as units of length. So they're just how far along you are around the circle. That's what radians are. So theta dot has units of radians per unit time. We're just going to write that as per unit time. And r dot has units of length per unit time. These guys are going to come together again, and we're going to get length times time to the -2. So again, we have the units of acceleration. So this term actually is dimensionally consistent. And this is the Coriolis term. So the Coriolis effect originates from this term. So how about this term over here? Let's have a look at this. This is r times theta double dot. Well, r has units of length, so that is consistent so far. What about this over here? We're taking the time derivative of the angle twice. And if we differentiate twice with respect to time, we're going to introduce 2 factors of time in the denominator. That's going to give us time to the -2. So this over here is where the length comes from, and this angle being differentiated twice with respect to time is where this factor of t to the -2 comes from. So this is consistent. So all 4 terms in this expression in polar coordinates for acceleration are consistent. We have done dimensional analysis. We have performed dimensional analysis and we found that all of the terms are consistent. If you add 2 terms together, the units have to match. Otherwise, you're going to run into trouble and things are not going to have physical meaning. You could write any expression you want. You can make the units whatever you want, but that doesn't guarantee that it's actually going to give you something that is physically meaningful. The reason we care about units is because they ensure that the quantities are physically meaningful. We want something that we can measure. We want to be able to do an experiment with it. And that's why units are so important. So keep in mind, there are some nuances. You have to be careful with units. Sometimes we don't care about the units. Sometimes we do care about the units. When we're trying to measure things, we definitely care about units. And these are quantities that can all be measured. If you have a particle that's moving in a two-dimensional universe, like this whiteboard over here, with some two-dimensional plane, all of these terms need to be considered. If there's changes in the radial distance and in the angle, you need to consider all of these terms. And polar coordinates are a fantastic coordinate system if an object is moving around some sort of central origin point. So we've examined the units and they all match, and that is the core message of this video. Make sure to play around with these units and try and experiment and see if you can make sure that these guys are all dimensionally consistent. In the next video, we're going to continue working in the two-dimensional plane. So make sure to find that video in the quantum mechanics playlist. You can find it if you click over here.